So right now we are going to see the proofs for the formulas in the lesson sets. So let's see. Uh, See, there are three formulas which we mostly will deal with. The first one is n of A union B is equal to n of A plus n of B minus n of A intersection B. Let's see how to prove this formula. This is very easy. So suppose A and B are two finite sets. What are finite sets? Finite sets are sets in which we can actually count the elements. So for example, if this is a universal set, you have this one set, consider this to be a complete circle, and this is another one. So we see that the between blue portion is supposed to be the intersection. Now this is A minus B, the red one, and the yellow one is B minus A, while in between you get the A intersection B. We are aware about this. Now look at it. Uh, how can we represent this? So can I say that A union B is equal to A minus B plus A intersection B plus B minus A. If you put all this together, you will get A union B, all the elements of A and B together. Correct? Now to write the same thing in the form of number of sets in each. So how will you write this? N of A union B is equal to n of A minus B plus n of A intersection B plus n of B minus A. It's very easy, right? It's not difficult at all. Now on the RHS, we are going to make a small change. We can plus and minus A intersection B on the RHS. That's not going to get any change to the equation that we have here. Now, if you add n of A minus B plus n of A intersection B, what will you get? N of A minus B and n of A intersection B. So, if that is together, just see what will you get. That blue and the yellow, red together, that will be the entire A, number of elements in A. Similarly, n of B minus A and n of A intersection B, that is the yellow and the blue together. That will get you the that will give you the n of b. So how it will look like now? N of A union B will get you n of A plus n of B minus n of A intersection B. So this is how you prove the first theorem, the first proof so-called in sets. Let's look at the second one. Second one is very easy. We do the second proof right from the first proof itself. See, this proof is if we have two sets and these two sets are not intersecting, they are disjoint sets. Obviously, when there is no intersection, the elements of intersection or the set that will form with the intersection will be a phi or a null set. So there is no intersection. So we will get A intersection B equal to phi. Thus, even if you use the previous formula that we did, which is n of A union B is equal to n of A plus n of B minus n of A intersection B, what do you get here? You'll get A intersection B is equal to phi. That is why if you just substitute the formulas, we will get if these two sets are disjoint, then n of A union B is equal to n of A plus n of B. Now these two formulas are extremely important. We are going to use these two formulas. Okay, the next formula we are looking at is n of A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C plus n of A intersection B intersection C. Yes, the formula looks pretty long, but when you actually try to use it with the given figures, it's not so difficult. Okay, the previous two formulas that you can see the box below are the ones which we are going to use them, primarily the first formula. You have to be very careful. The terms are new here in this particular lesson, plus the union and the intersection signs sometimes might just create a little bit of confusion just because you are using it for the first time, but once you get used to it, it's not very difficult at all. Okay, here we are going to consider three sets. Okay, suppose this is the universal set, and we're going to consider three sets. So let's say this is set A, this is set B, and this is set C. Now if you try to take all, this is how it's going to look. I hope the colors tell you very clearly the intersection of each set, right? Now we in A union B union C. Okay, first thing understand, in A union B union C we are talking about elements in all the three sets, right? Here B union C, consider that as one item. Like if you take A union B union C, you can take A B union C just like X, one single item. Okay, look at the first formula. What is the first formula here in the box below, black one, which is n of A union B is equal to n of A plus n of B minus n of A intersection B. That formula we are going to apply considering A union B union C as a separate item, single. In your mind, even if you can see two alphabets here, consider that as a single variable. So if you do that, what will you get here? N of A plus N of B union C. B union C is a single item here, okay? Minus N of A intersection B union C. We haven't done anything. We have only implemented the formula here. We have substituted the formula values in the formula. Now, N of B union C. I have already marked it red in color because we are again going to apply formula number 1 on that red color bracket that we have put in there. The other things remaining same, which is the N of A remaining same and the end of the formula remaining same, equation remaining same, sorry. Just look at the red color bracket. I have split that bracket completely using the first formula. So which will give you N of B union C will give you what? N of B plus N of C minus N of B intersection C. A simple substitution of the formula that we have. Now look at the last part. Which one? N of A intersection B union C in the bracket. We can apply the distributive law there. What is the distributive law? A of A intersection B union C. The distributive law says it will be A intersection B union A intersection C. Correct? The n remains there because that's how the whole equation goes. So it will be n of A intersection B union A intersection C. Look at that. Now again we are going to apply the first formula. A intersection B union A intersection C. It's a union formula again. So we can apply the union formula. What will you get? N of A intersection B plus N of A intersection C minus N of A intersection B intersection A intersection C. Just look at it carefully, and you can, if you try to write it yourself, you will get it. So let's say this is statement 2. Now the last part, which is N of A intersection B intersection A intersection C. If you look at that, that will give you the, if you actually look at this colored figure at the end, the center color, blue color, A intersection B intersection A intersection C, that is the blue color thing in between the figure that we have on the side, which is actually A intersection B intersection C, the intersection of all the three sets. So we can substitute it with that. Now let's put everything, statement 1, statement 2 and statement 3 in the formula. So just by substitution, what do you get? Look at that. N of A union into bracket B union C is equal to N of A plus N of B plus N of C minus N of B intersection C minus, now there's a bracket and inside the bracket we have n of A intersection B plus n of A intersection C minus n of A intersection B intersection A intersection C. If you open this bracket, everything that is there inside the bracket will change the signs. So now, if you open the bracket and apply the formula for the third equation that we did, if you apply at the end, you finally prove the formula, which is n of A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C plus A intersection B intersection C. This is not difficult. Write it yourself. Do it once or twice. You will get it. All right. Bye-bye. I'll see you in the class.